Wait, stop for 1 second before you do anything else. Somewhere in Shenzhen, China, right now, there is a room full of machines that are not supposed to exist. Not science fiction, not supposed to exist. I mean, the United States government spent 5 years, billions of dollars, and its entire semiconductor export strategy specifically trying to make sure this room could never be built. And 10 days ago, that room got tested. Independently. On the same international benchmark that has ranked the world's fastest computers for 33 straight years. No self-reported numbers. No marketing claims. A verified, audited score, submitted in front of the global supercomputing community in Hamburg, Germany. The result knocked America's #1 supercomputer, El Capitan, built at a U.S. national laboratory, the machine the Department of Energy treats as a strategic asset, straight down to second place. Here is the sentence that should stop you cold. Inside this Chinese machine, there is not a single Nvidia chip, not one AMD chip, not one Intel chip, not one component sourced from any Western supply chain anywhere in the system. Every processor, every cable, every line of operating system code engineered inside China. The machine is called LineShine. And before I explain how it works, I want you to answer one question honestly in the comments below, right now, before you keep watching. Do you think 5 years of American chip export controls made China's technology weaker? Or did they accidentally force China to build something the controls can never touch again? Drop your one-line answer. I read every comment, and at the end of this video, I am going to tell you exactly where I land, because after researching this for days, I have a very specific opinion, and I think it's going to surprise some of you. Now let's get into what actually happened here, because the real story is stranger, more technical, and more important than the headline. Let's start with the place, because the place tells you everything about why this was not a lucky accident. The National Supercomputing Center in Shenzhen, NSCS for short, sits inside Guangming Science City, a purpose-built research district the Chinese government has been constructing for years specifically to house projects exactly like this one. This is not some backroom operation. Public infrastructure records show the facility itself represents an investment north of 8 billion Chinese yuan. That's well over $1 billion US. In civil construction and machinery alone, before you even count the processors running inside it. NSCS has existed since 2009. It has previously housed machines that cracked the world's top 3. It sits in a city that is already home to Huawei, DJI, and a dense cluster of hardware engineering talent that most Western analysts consistently underestimate. This is not a lab that appeared out of nowhere. This is an institution with a 17-year track record that finally had the components, the funding, and the political mandate to swing for the top spot. The system was built by the Shenzhen Cloud Computing Center, working directly with NSCS, and the chief designer, the person who stood on stage in Hamburg and walked the world through exactly how this machine works, is a woman named Lu Yutong, director of the National Supercomputing Center in Shenzhen. Here's what I find remarkable about her presentation. She didn't oversell it. She described the design philosophy using 3 principles she called ABC: application-driven, balanced architecture, and co-design on full stack. In plain English, don't build something powerful for the sake of a headline. Build something that actually solves the specific computing problems China needs solved, using every layer of the stack working together instead of parts bolted on afterward. That is not the language of propaganda. That is the language of an engineer who has spent years thinking about a problem most Western labs assumed was already solved by simply buying more Nvidia GPUs. And back in April of this year, Lu Yutong's team already told the world what they were building. Most Western coverage either ignored the announcement or quietly labeled it unrealistic. 10 weeks later, LineShine submitted verified results to the TOP 500 list. It debuted at #1 on its very first appearance. 9 years since a Chinese machine last held that position. The last time was Sunway Taihulite, back in 2017. That's not a stunt. Standing up and predicting an outcome that experts privately doubted, then proving it on the most credible leaderboard in the field. That's engineering discipline most companies never achieve even once. There's one more piece of context that matters here, and it rarely makes it into the coverage. The LX2 processor at the heart of LineShine appears to have been co-designed with Huawei, reporting points toward Huawei's HiSilicon chip division specifically. That partnership matters because Huawei has spent years under some of the tightest restrictions the United States has ever placed on a single company, and it kept building anyway. If Huawei's chip design expertise fed directly into the processor now sitting inside the world's #1 supercomputer, that tells you something about how these restricted companies have been quietly redirecting their engineering talent into exactly the kind of project we're looking at right now. This isn't one lab working in isolation. It's the output of a much wider domestic ecosystem that's been forced to mature faster than it otherwise would have. Let me give you the scale, because the scale is where this stops sounding like a press release and starts sounding like an actual engineering achievement. Roughly 45,000 custom processors, called LX2 chips, spread across more than 20,000 compute nodes. Each LX2 carries 304 cores, built on the ARMv9.2 instruction set, running at 1.55 GHz. Total core count across the whole system, 13.79 million cores, all coordinated in parallel. Compare that to El Capitan, America's previous number one, which runs 11.34 million cores. LineShine has more cores. But raw core count alone doesn't win benchmarks. If it did, this would be a solved problem and everyone would already be doing it. The interconnect linking all those cores together is called LingQi, a proprietary Chinese-designed networking fabric delivering roughly 1 microsecond of latency between nodes. The whole system runs on Kylin OS, a domestically developed Linux distribution built specifically for deployments exactly like this one. Here's the number that actually tells you whether the system works or whether it's just an expensive pile of silicon. Computational efficiency, 80.35%, meaning the machine achieves over 80% of its theoretical mathematical maximum in real, sustained operation. For comparison, Japan's legendary Fugaku system, widely considered one of the best engineered supercomputers ever built, runs at 82.3%. LineShine landed within 2 percentage points of that gold standard on its first public benchmark at a scale roughly 5 times larger. The verified score itself, 2.198 exaflops of sustained performance on the LinPack benchmark, the same standardized test that has ranked every major supercomputer on Earth since 1993. That's more than 2 quintillion calculations every single second. El Capitan's verified score on the same test, 1.809 exaflops. LineShine beat it by roughly 22%. And LineShine didn't just take the top spot on the main list. It also took number 1 on a separate ranking called HPCG, which tests a different, more communication-heavy style of computing workload, posting a score of 22 petaflops there as well. That's not a machine optimized to win one narrow test. That's a machine that's genuinely strong across multiple different measurement styles. I want you to sit with one more number before we move on. Total power draw, 42.2 megawatts. We'll come back to that number because it matters. And I promised you at the start of this video that I would give you the honest picture, not just the impressive one. Now here's the part almost nobody explains correctly, and it's the part I find genuinely fascinating. Every major supercomputer built over the last decade leans on GPUs, graphics processing units, because GPUs can run thousands of simple calculations in parallel, which is exactly what massive scientific simulations need. That's the entire reason Nvidia became one of the most valuable companies in history. The unwritten rule of high-performance computing has been, if you want to compete at the top, you need GPUs. Full stop. LineShine has 0 of them, just CPUs. The same basic category of chip sitting inside your laptop, scaled up to 45,000 of them, engineered specifically to close the gap that normally makes CPUs lose to GPU-accelerated machines. So how does a CPU-only system beat the best GPU-accelerated machines on Earth? The answer sits inside the LX2 chip itself, and it comes down to one specific bottleneck that every large computing system fights against: the time wasted moving data back and forth between the processor and its memory. In most systems, memory sits some distance away from the compute cores, connected by a bus, and every time the processor needs data, it has to wait for that data to travel across the board. At the scale of a supercomputer running millions of cores simultaneously, that waiting time compounds into a massive, invisible tax on total performance. The LX2 design attacks this directly. Each chip uses a chiplet architecture split into 4 separate compute domains, and each domain carries its own slice of high-bandwidth memory sitting physically on the chip package itself. Not across a bus, not on a separate card, but essentially inches away from the cores that need it, with a dedicated data movement engine shuttling information between that fast on-package memory and a much larger pool of off-package memory for bigger workloads. On top of that, the chip integrates dedicated matrix math acceleration units directly onto the core itself, the same category of specialized math circuitry that gives GPUs their edge on certain workloads, instead of keeping that acceleration on a separate add-on card the way traditional systems do. Lu Yutong described this choice herself on stage in Hamburg. Her words, paraphrased. The goal was matrix acceleration integrated directly on the core, dramatically cutting data movement overhead while keeping the system easy to program. That's the trick. Not more chips. not brute force alone. A fundamentally different memory architecture that closes the specific gap GPUs were built to solve, combined with a custom interconnect that keeps nearly 14 million cores talking to each other without drowning in their own communication overhead. Solving that coordination problem at this scale, on a first attempt, with over 80% efficiency, is a genuinely difficult engineering accomplishment, completely separate from the political story everyone else is focused on. And I want to pause here for the mid-video moment, because if you've made it this far, you already understand LineShine better than 90% of the headlines currently circulating about it. That's exactly the standard I try to hit on every iron circuit video. Not the surface level headline, but the actual mechanics sitting underneath it. If that's useful to you, the subscribe button is right there. And I promise the second half of this video is where the story gets genuinely uncomfortable for the people who assumed export controls had this handled. Let's keep going. I respect you too much to give you only the flattering half of this story. The TOP 500 list actually runs two separate benchmarks. The one we've been discussing, LINPACK, or HPL, measures full double precision math, the traditional standard for scientific supercomputing. The second benchmark, called HPL MXP, tests mixed precision math, lower precision calculations, which is much closer to the kind of math that actually trains large AI models. On that second benchmark, LineShine did not finish first. It finished fourth. Its score there was 7.92 exaflops, only a 3.6 times jump from its main score. GPU-accelerated machines like Capitan get a dramatically larger boost when they shift into mixed precision, because that's precisely the workload GPUs were engineered around from the start. Multiple outlets covering this story, including Reuters, have specifically flagged that TOP 500 placement does not equal leadership in AI-optimized computing, and industry analysts have been quick to separate the two. There's a second honest weakness. LineShine draws 42.2 megawatts of power to hit its number. Capitan draws roughly 30 megawatts for its result. That means LineShine is currently the least power-efficient machine in the entire top 10 of the world rankings, even while holding the #1 spot outright. Beating the competition and doing it efficiently are two different achievements, and right now, LineShine has only proven the first one. So here's the honest, unhyped version. LineShine is not, today, a machine that trains the world's most advanced AI models faster than America's GPU clusters. On that specific race. The race that actually determines who builds the next generation of frontier AI. American accelerator-based architecture still leads, and that lead is real. Even Jack Dongarra, the Turing Award-winning computer scientist who co-founded the LINPACK benchmark itself and has watched this leaderboard for over 3 decades, was careful in how he framed it. He called LineShine's result evidence of very substantial capabilities in processor design, while explicitly cautioning that one benchmark is not a complete measure of technological leadership. He pointed out that scientific application performance, energy efficiency, software maturity, and reliability all matter just as much as a single headline number. I think that's the right way to hold this. Not dismissing it. Not overselling it either. Here's where I think most of the coverage on both sides is getting this wrong. China built a CPU-only machine, not because CPUs are secretly better than GPUs. Every engineer on this project knows they aren't, for AI-specific workloads. China built it this way because it had no other choice. United States export controls have specifically restricted China's access to Nvidia's top-tier GPUs and AMD's most advanced accelerators. The exact hardware categories that power Capitan, Frontier, and every other GPU-based system on that leaderboard. Faced with that wall, China had two options. Keep chasing workarounds for banned hardware and stay permanently dependent on decisions made in Washington. Or ask a completely different question. Can we reach the absolute top of global computing using only what we're allowed to build ourselves? LineShine is the verified answer to that second question. And here's why the honest weakness on AI-specific math actually makes the achievement more significant, not less. That mixed precision gap is not a wall. It's an engineering problem, and engineering problems get closed with iteration, not luck. What China now has, for the first time, is a fully domestic Exascale system running real production workloads today. Not a lab prototype, not a paper design. Real scientists are already using it. A researcher at Tsinghua's Shenzhen campus, Haohuan Fu, has used LineShine to combine physics-based weather models with AI to test a full decade of rainfall predictions across East Asia. Work that took just over 14 hours on this machine, work that would take far longer on typical clusters. That's not a benchmark stunt. That's an actual scientific workload already running at scale. Every hour that machine runs, China's engineers are learning where the LX2 architecture struggles, where the Linghui interconnect bottlenecks under real load, and exactly what needs to improve in the next generation. That kind of operational experience compounds. It cannot be bought. And critically, no export control anywhere in the world can take it back once it exists. Intersect 360 research co-founder Addison Snell put it plainly. He expects LineShine's ranking to create a ripple effect across the US, Europe, and Japan as the AI compute race continues. Not because the AI gap closed overnight. It hasn't. But because the assumption that export controls could permanently cap China's ceiling in advanced computing just took a very public hit. I've been covering China's technology build-out on this channel for a while now, and I keep watching the exact same shape repeat itself. Back in 2019, the United States effectively pushed China out of competing at the top of the TOP 500 list by cutting off access to the advanced GPUs needed to compete on that stage. China went quiet on that specific leaderboard for years. Plenty of Western analysts read the silence as decline. The silence was never decline. It was development happening somewhere the leaderboard couldn't see. Glass substrate technology, the material now replacing plastic underneath advanced AI chips. Advanced quietly while the world's attention stayed fixed on lithography machines. DeepSeek shocked Silicon Valley by training a genuinely competitive AI model built by a team that Western analysts assumed needed American-grade compute it didn't have access to. Chinese-made memory chips started showing up inside consumer hardware from companies most people trust as reliably Western. And now, LineShine. Years of silence on the world's most watched supercomputing leaderboard, followed by a first attempt debut straight at number 1, verified by the same benchmark that has run for over 3 decades. Every single time, the pattern is identical. A restriction gets imposed. The restriction redirects investment and engineering focus somewhere the restriction can't reach. That redirected investment eventually produces a capability that would not have existed at all without the original pressure. And once that capability exists, it no longer depends on anything anyone else can take away. I want to be careful here, because I'm not interested in cheerleading for any government's press release. The verified benchmark score is sitting on TOP 500's official site right now. Anyone can check it. The efficiency numbers are public. The independent commentary from Dongara, from Intersect 360, from Reuters and Nature, all point in the same direction. This is real engineering, with a real, specific, honestly disclosed weakness on AI training math that America still leads on today. But today is doing a lot of work in that sentence. The question that actually matters is what happens over the next 3 years. Whether China's domestic accelerators close that mixed precision gap, whether the next generation of the LX2 architecture folds in better low-precision performance, whether the CPU-first approach eventually merges with China's AI accelerator programs into something that competes on both fronts at once. That's the story I'm going to keep tracking on this channel, video after video, as it develops. It's also worth remembering that China stepped away from publicly submitting its most powerful systems to this leaderboard for several years, choosing instead to maintain its own separate domestic rankings. That means LineShine is very likely not the only Exascale class machine China currently has running quietly in production somewhere. It's simply the first one they chose to put back in front of the entire world, on the one benchmark every serious computing nation still respects. That alone should change how confidently anyone assumes they know the current state of China's total computing capacity, because the public leaderboard was never showing the complete picture in the first place. So here's exactly where I land after spending real time with the primary sources instead of just the headline. LineShine does not mean China has won the AI race. I won't pretend it does, and anyone telling you that is skipping the mixed precision numbers on purpose. On the specific math that trains frontier AI models, American GPU-accelerated systems still hold a real, measurable lead today. But I think the people waving this off as a political stunt are making the mirror image mistake. They're staring at today's gap and completely missing tomorrow's trajectory. A country that just proved, on a verified international benchmark, that it can build a top-ranked Exascale supercomputer entirely from domestic chips, domestic interconnects, and domestic software has built something more durable than a single leaderboard entry. It has built a foundation that cannot be switched off by anyone else's export policy, a real operational learning curve that starts compounding the moment real scientists start running real workloads on it, and hard proof that its domestic chip ecosystem can reach the absolute frontier of computing when it has to. That's not a temporary headline. That's a structural shift in how this technology race is going to play out. The export controls were built around one core assumption: that permanent dependence on Western hardware was the only path to the top of global computing. LineShine is a very public, very verified argument that the dependence was never permanent. It was just the path of least resistance, right up until it got blocked. Now here's my actual ask, and it's a specific one, not a generic "please subscribe." If you watch this whole video, you now understand exactly what LineShine achieved and exactly what it still can't do, which puts you ahead of almost every headline currently circulating about this story. That's the standard for every video on this channel. The glass substrate story, the Chinese memory chips showing up in Western products, the Nvidia export battle, the DeepSeek moment. Every one of these connects into the same larger picture of how this technology race is actually unfolding, piece by piece, underneath the headlines. The next video ties all of it together. Every thread we've covered on Iron Circuit into one complete map of where the chip war is actually heading over the next decade. You don't want to miss that one. Hit subscribe now and turn on notifications so it actually shows up when it drops. And go back to that question I asked you at the very start. Did 5 years of export controls make China weaker, or did they force China to build something that can never be restricted again? I've got a firm answer to that after all this research, and I genuinely want to see where this community lands before I tell you mine. Drop that comment. I'll see you in the next one.